what's called measures of variation. Yesterday we looked at measures of center, which were the mean, the median, and the mode. And now these things called measures of variation essentially just tell us how spread out data is. Okay, how spread out data is the issue here. Because you can have a real skinny spread, in other words, all your data or then just a few values, or it can be real fat and your data be, you know, all over the place, so to speak. The first measure of variation is called the range, and it's not really that useful in statistics, but it's a good one just to kind of get an idea. And it's basically the range is just the difference between the highest and the lowest data value. So I've got two sets of data here. One for San Francisco temperatures. So in this case, if you look along there on that, right above that, you'll see that the highest value is 63. And then the lowest value, and the 63 is in September, and then the lowest value is in January, which is 51. And so we just subtract, and that gives us a 12, value of 12. Now, what does that mean? Well, that's the whole kind of thing and why it's not so useful. You can use it to compare. So like if we wanted to do the same thing with New Orleans average temperatures, those were average temperatures. And these are average temperatures, which don't necessarily mean that much. I mean, so much. But, you know, it's looking at throughout the whole day if you average them. So again, here, the highest one looks to be right around June or August, and we're going to call that 81. All right, and then the lowest one, it looks to be January, which looks to be 61. And you know what I want to say, and it's not that important. I think this is actually 82. Yeah, and then that one, because that one's about half as, I'm sorry, it's not 60, it's 51. 51. So then if we subtract, we've got 31 is our range. Now, if you compare the 12 to the 31, then you got more of a meaning to things. So what does it essentially say in that during the year in San Francisco, the temperatures basically stay within a 12 degree range all day throughout the year. And in New Orleans, it's got more variation. So we've got 31 degrees variation. All right. So you got more seasonal change, you could say, throughout the year here than you would in a place like San Francisco. Now, as I had said, is the reason why this one is not so useful in statistics is just that there's no real like I said, it's no real standard to it. Well, what is low and what is high? But if we have this other one, which is called a standard deviation, things are a little bit different. And this is a very, very useful, and it's the linchpin of most of statistics, not just this course, but Math 203, which some people might take next, which you deal with the standard deviation quite a lot there. Standard deviation is something that's used throughout the course. Now, there's two different standard deviations. We have to keep that in mind. The standard deviation just tells us how the data differs from the mean. All right, how much different it is from the mean. And when it's called a standard deviation, what it's going to do, it's going to put it in terms of, for the most part, the range can be between -3 and 3. It can be lower and higher than that, but for the most part, it stays between -3 and 3. So every piece of data that we would look at is going to be between 3 standard deviations from the mean, one side or the other. Well, what does that mean? Well, it just kind of, the term standard means that we can use that standard deviation value to tell us important things about any data set. As long as it's using the same, as long as we're comparing the standard deviation of one set of data to the other. But as I said, there's one for the sample, and there's one for the population. Now remember what I said, the sample is a subset of the population. Sometimes the population can be small and accessible, but oftentimes the population is going to be rather large, and the sample is a subset of it, and it's on that way on purpose so that we can make it manageable and that we have a sample that's reflective of the population. And so just working with that is going to help us find out what we need to know. Now, I'm going to do this on the board here. We're going to do 2 of them just to kind of get, and there's not really that much difference between the 2. There's one slight little difference we got to remember. I guess I'm going to have to do it on here because I can't really think how to draw straight lines on that other one. I'll just go over here. I'm going to write. Now you remember from the mean, that little symbol right there that I just wrote right there, it's sigma is what that's called, capital sigma. And that just means, mathematically, it means sum. So what we do is we break it down into a process. And of course, you know what n is. N is just the number of items in your data, in your sample or your set. That's what we learned in chapter 2. So we subtract, so for the sample, we're going to take the mean and subtract it from every one of the pieces of data. We're going to square those and then add them up. So I'm going to do it on this little chart because that helps things quite a bit better, I think. The way that they show you in the hearing some kind of, might be coming from my laptop I had open and that didn't go off. It doesn't matter though, really. All right, let's see if we got enough here. We might have to draw a, yeah, I'm not going to do that. All right. So we're going to put here is X. And so what I'm going to do here is I'm going to just write those pieces of those values. And I prefer to do it like this, the way that Alex does it. I think it's slightly confusing. If you can figure it out, more power to you. I just don't like it. I like to do it in this fashion, where I've they kind of do it horizontally and do it in parentheses. And this is going to be x minus x bar. So what we got to have first is we got to have the mean of this data. In other words, we got to have that. We got to add them all up. And so if we add all those up, hold on a second. Oh, I know what that is. I had some video playing in the background. Okay. So we got to figure out what the total of the data pieces are. So it's 8 plus 18, 8 plus 10. So this is 54 total. And I'm just adding all those up. And then there's 1, 2, 3, 4. 1, 2, 3, 4, 5. There's 6 of them, right? And so this is going to be a nice, neat one. It doesn't always end up like this. But there's no rounding involved on this one. And that's going to make that first one, a good, nice, straight example. Now, what we're going to do is we're going to subtract 9 from every one of these. So 8 minus 9 is -1, correct? 10 minus 9 is just plain old 1. 13 minus 9 is 4. 11 minus 9 is 2. And both of these are going to be the same. 6 minus 9 is, these are both -3. Now, this is a checkpoint, you can say. And what that means is if everything has been done right, including calculating the mean and doing the subtractions, then these should add up to 0. And they do. So you don't really need that for anything, but the sum of those should always be equal to 0 if everything has been done correctly up to that point. Now, the next one is we got to square those things. So -1 squared is going to be 1. Anything squared is always going to be positive, even if it starts out negative. Okay. So both -1 and 1 are positive 1. 4 squared is 16. 2 squared is 4. All right. No, we don't really need that other column. Hold on a second. Let me just check something. All right. So I'm going to use this column. I probably could have put here, I could have just put the 8 minus 1 for you in this one and moved everything over. But all right, now the thing we need is the summation of all these. That's what this is up here, that whole numerator. All right. All right. So S is equal to the square root of 40. And as well, I didn't quite say it, but n is equal to 6. So for the sample, that's the one thing that's different, is we got to subtract 1. I'm not going to really explain why, because I don't really think you need to know. You just needed to remember that. But it has to do with the correction factor. And generally speaking, we always want to go one decimal place out from, so we got whole numbers. So this is going to be 2.8. So we just go one place beyond. In general, if you're not told what to round to, okay. So here is the sample standard deviation for that data right there. All right, any questions about that? We're going to go through another one, like I said, and it's only got one little tiny difference. So the procedure is the same, except for instead of using n minus 1, it's going to have n down there. All right. So for the population, it's called sigma. That's not a 6. It's a baby sigma, lowercase sigma. All of the population parameters and statistics. They all use Greek symbols. So that's n right there. All right. So we'll do one more with this slight difference. And I'm going to put the same number of rows and columns, and I'm actually going to use, how many do I have? And I'm actually going to use all of them this time. I'm actually going to have one more still than I need. Well, the first thing we need to have is the mean. And in population terms, it's called mu. That's not a U. It's a fancy looking U. It's called mu. But it's the same calculation. So when you add all those up, and then this 1, 2, 3, 4, 5, 6. It's always for the mean. It's always however many pieces of data. It's always. So this is 26. All right. So we're just subtracting 26 from everything. So this is -2, another -2. This is 0. 26 minus 26 is 0. It's 3, another 0, and 1. All right, and again, if you add all these up, you get sum of 0. That will always happen with these values, and because that's what they call the deviations. See, -4, and then 3 and 1 is also 4, so 0. All right. So these are the ones I want. I actually put another extra column in here. I had 4, and over here I put a 5 for some reason, but I don't need that one. So I'm going to add all these up. So that's 8. So that's 18. Tell me if I'm wrong, but that looks right. So that's 9 and 1 is 10, plus 4 is 14, 18. All right. So the sigma, or the Standard deviation for this population is 18 divided by 6. Now, this is the one place where it's different. Everything else is exactly the same. The only thing that's different is now for the population, we're dividing by n, the total number of pieces of data, whereas over here, for the sample standard deviation, it was one less than 6. It was 5. Here's another one that's coming out nice and even. So this is like, what is that? That's 1.7, I believe. All right, so that's 1.7. And generally speaking, you can compare these amongst each other. And like I said, is larger standard deviation means that there's the data is more spread out. See, with this, they were all relatively close, like 26 was the mean. Everything was within 3 of the mean. This one was a bit larger. The mean was 9, and it went out to 4 more than the mean. Plus 13 is 4 more. Well, you can see them here. So that's the standard deviation, both the sample and the population standard deviation in one shot. All right. Percentiles. Percentiles is just a fancy way of saying percents. If you had 100 pieces of data and you had them all sorted and you wanted to find the 75th percentile, you would just find the 75th one from the left, and that would be your 75th percentile. All right. But usually you don't have, not such nice and neat ones like that. So, for example, on this one, well, you can see visually that if you are smarter than, or if you're in the 80th percentile, then that means, you're smarter than 80% of those that are below you. So that blue U right there represents the 80th percentile because it's the margin of everything 80% to the left. That also means then up here is 20%. These other ones would be the 20% because it's essentially the complement rule that they have to add up to 100 or 1 or 100%. All right, so we want to find two things. We want to find the 21st percentile and the 63rd percentile. All right, so here's the data we got. And to just kind of save time, I already sorted it for us because that's usually the hardest part to do. And writing it down on the board is going to take even longer. But this data right here is this data sorted. So in order to find a specific percentile, then we need to order the data least to highest. All right. Now, what we're going to do is to get the 21st, oops, I should have asked you something first. How many pieces of data are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. And my writers are 20. Let me count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 pieces of data. In other words, n is equal to 19. That's like a cardinal number from chapter, the first chapter. All right. So to get the 21st percentile, we multiply 19 times 0.21, which is just the decimal equivalent. All right. The decimal equivalent of 21%. Because we need to have percentages in decimal form in order for them to work, in order to do any math at least. And I'm going to multiply that out. And that's going to give us 3.99. Now, here's the clue that tells us, because we're going to use this number here to help us find the position that's above 20, that's 21st percentile. So round up any partial values to the next whole number. Therefore, the 21st percentile is in position 4. So 1, 2, 3, 4. All right. That's the way it works. It's that simple. Now to do the other one, I'm just going to copy this and change a few things. To get the 63rd, come back and see what that is. So I'm just taking out the ones for the last thing. All right, so now, wait, what happened? Something strange happened. Oh, I was changing the wrong one. Guess I should have just copied it once I was trying to change the second one. I'm just trying to save myself some work, and I end up goofing up. So 19, and that's the n, times 0.63. So it's 11.4. All right, so now when we multiply the 19 times 0.63 for 63%, we get 11.4. So now it doesn't matter whether, it's above 0.5 or below 0.5. We always bump it up to the next whole number. So what's in the 12th position? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 22 is the 63rd percentile. All right, any questions? So the key is once you do the multiplication by whatever percentile is written as a decimal, you bump it the data to the whole number, next whole number, and then in the sorted data, you just count that many over. All right, so I think I told you last time that the mean, median, and the mode being the measures of central tendency, if they're all three the same or very close to being the same, that's usually what we call normally distributed data. So it has this shape here. And as I said, for the most part, standard deviations are between -3 and 3. They can get larger, but they're very rare, very, very, very rare out there. And they can get smaller than -3, but they're very, very rare. For the most part, they're going to be in between -3 and 3. But as I had said, when this data is normally distributed, or what we call a symmetrical data set, the mean, median, and the mode are very close to being the same. They would never in real life be exactly the same, but that's in a perfect world, they would be the same. Now, if we have data that we know is that normally distributed data, then we can use something called the empirical rule. Now, what the empirical rule states is that for normally distributed data, if we go one standard deviation on either side of the mean, in other words, from here to here, from here over to here, that's 68% of the data. Sometimes there's I think this one's actually a little bit better. That's the one from our book, I believe, but I don't really like it that much. So I'll just kind of show you another one that really is the same thing. And you can see it a little bit better graphically. So one standard deviation on either side of the mean is 68%, and that's the purple area looking at it here. Up here, it's the one that's red. But like I said, is with this one, the way they have it colored, it's a little bit easier to see. And since the data is symmetrical, the mean is the halfway point. That means you got 50% on the left and 50% on the right. So that's why they have this 34 and 34, because that's half of 68. All right. So the purple area, one standard deviation on either side of the mean is 68. If we go out two standard deviations, 1, 2, 1, 2 from the mean in both directions, that's 95% of the data. from here over to here. That's 95% of what's underneath that curve. All right. So from here, where the green and the orange change, to over here to where the green and orange change, is 95%. Now, they've got it broken up into these little blocks, and this can be helpful to let you see, because if you got 68% here, then to get to 95, is 27. So 27 divided by 2 is where that 13.5 comes from. So this one shows you just a little bit more, and this could be useful for answering some questions. So just realize that it's in here if you want to, just a little bit different perspective, because this is the one that they show you in the book. And then if we go out to 3 standard deviations, we have almost all of it for all intents and purposes. It's 99.7% of the data from -3 to 3, as I had said. -3 to 3 is almost all, or 99.7. Now, that means that you got this additional, remember, it's 95 and then almost all, it's not 90, it's not 100%. It's essentially 4.3% to get out to 99.7. If it were 100%, it would be 5, but it's not quite, so it's 4.3. I'm sorry, 4.7. And then the 4.7 divided in half is that little yellow in that little yellow part. So that being said, we can use the empirical rule to help us know with normally distributed data how much is in between specific data sets. So for example, all right, it says here, distribution of SAT scores is scaled to be approximately bell-shaped with a mean of 500 and a standard deviation of 100. So about 68% of scores are between what? Well, since that's one standard deviation, so the mean is 500 and the standard deviation is 100. So for 68%, the boundaries are 500 minus one standard deviation, which is just 100, and 500 plus 100. So the boundaries for 68% are 400 and 600. So 68% of the scores for SATs will be between 400 and 600. We can do the same thing with 95%. That's 2 standard deviations. So 2 standard deviations is equal to 2 times 100. So 200. So for 95%, the boundaries are 500 minus 200, 2 standard deviations, 500 plus 200. Or what are they? They would be 300 and 700. All right. We're going to see the answer to this by simply looking at the graph that we talked about, that 700 is the upper boundary for 95%. So the answer to this third question is, if we've got a score of 700, then we're in the top 95%. In other words, you're right here. That's 2 standard deviations. So 700 would be right there. This is 600. That's 500, 400, 300, 200, and then this would be 800 over here, for instance. But they asked about 700. So if you're at 2 standard deviations above the mean, you're in the 95th percentile. Now, you don't always have standard deviations that are whole numbers. And so that's what we get. We have this thing called a z-score. Oh, and this right here is a neat little tool if you want to use it. Let's see something. I'll just kind of see if I can. What was it? Second one. Oh, it's 300 and 700. All right, I'm going to show you this, just kind of give you a visual idea of it. So the first one was 400 and 600. Where'd that little thing go? What's up? Yeah, that's it. So 1 standard deviation from the mean, that's what it looks like in terms of our data, 400 to 600, which is essentially, like I said, this would be 0, and this would be 1 standard deviation, and that's the mean, and then 1 standard deviation down, 1 standard deviation up. And then the other one was 300 to 700. And then they didn't ask us about it, but if we did all the way, 3 standard deviations, so it'd be 200 and 800. So that's almost all of it. But right here, if you're right here, then that's the 95th percentile. Better than 95% of everybody else. All right, so let's just move on. So the empirical rule is for when we got kind of more or less simple scenarios and you want to know when you're dealing with whole number standard deviations. But let's just say we've got a z-score of 1.18 and we want to find the area that's less than. Now, in your book, in the Alex, they've got 2 different ways to do this. They'll give you the access to a little chart to do it, and they'll also let you use the little calculator to do it. But I'm going to use that thing that we just used. show you this. We're looking for the area of that's less than 1.18. All right. So that's it drawn there, but how much is that area? Well, that's what these things can tell us. Either your chart or your book. I'm sorry, either that chart that's in your book, and like I said, they'll have a link for it in Alex, or they'll have that little calculator up there for you to use, which all does it. Just remember that they always are telling you how much is less than. So we were looking for 1.18 standard deviations. How much was below that? Well, that's how much there is. 0.881 or 88.1%. They're going to have you, it'll always come back as a decimal, but they may have you write it as a percent. All right. Now, if we want to find the area over here, all right, then we got to use the complement rule. I'm just going to type that out. And this is what they call a z-score. Standard deviation is called a z-score. 1 minus, and put was 0.88. So that's the complement rule. So this would be 0.119. So the percentage over here on this other side is 11.9%. Because remember, everything underneath there adds up to 1 underneath that curve. That's mirrors probability. So that's how we find out what's to the right of something, by subtracting the amount left from 1. All right. Now, for you know what? I wasn't sharing I was doing the typing out. So for finding the area to the right, in other words, this little part right here, you use the complement rule, because everything has to add up to 1 underneath that. It's essentially probability. Everything underneath there is 1 or 100%. So 11.9% is over here. And this little thing will show you that if we put above 1.18, and then show you the same thing, 11.9. And like I said, the calculator that you have in Alex, it's only going to do the below. It's also the same thing when you got the table in there. They'll only do below, I believe. I don't think they do above. So you got to just remember it's a complement rule to find above. Now, to find in between, we got to look up both of them, and then we're going to subtract. All right. So I got 2 z-scores here. I got 1. Well, I'm going to look up this one first because this is the larger one, 0.92. So if I look that up, .92, that's this amount here. It's 0.8882 1, 2. And I should have been back over here when I showed you, but let's go back. All right, so we're looking for between 0.992 and negative 1.25. Find this area. We look up both values, then subtract smaller from the larger. So that's the one that we looked up over there for the 0.92. That's going to be the larger one. And the other one is negative 1.25. Let's look that up. So I'm just doing the below to make it simple. So the below is this part. So that's 0.1056. So then if I subtract those, so it's always subtract the larger from the smaller. If you do it the other way, you're going to have a negative number. And you can just knock the negative sign off and it'll be what you need. But this should always be a positive number. All right. And then let's just go back over there and I'll show you that if we just do it directly with that for the visual effect, in other words, that thing I'm showing you with does above, below, and between. It was 0.92. So see that? That's what I have. 0.7156. But you can see the way that it works when you're calculating this by hand is you find everything from here on over, which was your big number. It was the one. It was 0.92, and that was the 0.82. And then when you look this one up, it's the smaller number. And so when you subtract it, you're essentially cutting that little piece off, and that tells you how much is in between. All right, so the last little thing deals with this thing called the z-score. How do we calculate a z-score? Like we were just handed some z-scores, but if we want to calculate one, this is how we do it. So z is equal to, and it's got a numerator and a denominator. In the numerator is whatever piece of data you want to calculate the z-score from. You subtract the mean and then divide by the standard deviation. All right. And that essentially puts it in its relative perspective on the graph. Where does that piece of data reside? So this university conducts placement examinations to all incoming freshmen. The examination scores of 1,000 examinees last semester were approximately normally distributed. We need to know that to do this, with a mean score of 80 and a standard deviation of 5. What is the probability that randomly chosen student got a score between below 70, above 82, and between 175? 75 and 90. So we're going to have to do all these on the board. And what I'm going to do is I'm going to use that other board because I can copy and paste this and I won't have to come back over here and look. Okay. Hopefully I didn't see you when you wrote it, but I figured out that I wasn't sharing something right. So hopefully I figured it. I did it. All right. So so let me put this in here and then I'll share this. All right. So I'm going to write over here that z-score formula. So what that means is that's x minus the mean divided by the square root is divided by the standard deviation. So probability of x is less than 70. We'll do that first. And that's what this amounts to. It's probability. Everything underneath that curve is 1. So when we're calculating this area, we're calculating probability. So 70 minus the mean and then the standard deviation was 5. So this one is going to be a whole number, but still, it's an application, and it doesn't have to end up being a whole number z-score. So less than 2. So what I'm going to do is I'm going to run over there and get that value for 2 standard deviations, and I'll bring it back. It's -2, actually. I'm just going to put the table. So we just got to remember that we bring that back, and that's the probability. Which is, what is that? about 2 point, so if they ask for it in percent, you just gotta remember to go over your 2 decimal places. Because everything calculation-wise is gonna always be a decimal, right? So if you want it in percent, you gotta count. You gotta convert it. All right. So this one is greater than 82. No, it's going to be equal to a probability. One minus the less than. So we're going to follow the same procedure, but when we get that probability back, we're going to subtract from 1 because it wants above. All right, so let's just calculate the Z is 82 minus 80. So what does that come out to? That's 2/5. This time it's positive. So that's 0.4. All right, so I'm gonna look that up and I'll bring it back. So this is equal to 1 minus, I gotta look that. That's a z-score, that's not an area. So let me go look it up and I'll bring it back. So it's 65.6554 below. So the probability then is that it's greater than 82 is 1 minus the probability of it less. So that's 34.46. Let me do the last one real quick because we got to do 2 of them here. All right, to do it by hand. We can have kind of cheat and use that that thing I was using, but you won't have that option. You have to do it by hand. So all right, so we got to do 2 z-scores. We got to do the one for 90 minus the mean over 5. So that's minus 80. So that's 10 over 5. So this is going to be a nice, neat 2. So this was for, like I said, this was for 90. And the other one was the 75. And then when we get to them, we're going to subtract the two. All right, so we got to find the two and bring them back and then subtract. So so the bigger one is the best one to do first because that's going to be the positive one. I mean, that's going to be a bigger number. The problem between these is and the other one was -1. And so it should be there we go. So there's about 80%, 1%, or 81 point, almost 82% would be between these two values. All right, well, that's pretty much it. We may have a few incidentals.